Right, good afternoon, everybody. Well, I thought I was going to need the extra 5 minutes, but it turns out that I. So we could go ahead and start on time. Let me start sharing my screen. Okay. Everybody seeing the screen? Everybody can see writing? Yes.
Yes, sir.
Nice. Good. So today we're going to look at the 3-phase tutorial. I trust that everybody did it.
Right. And
So just remember, reminder for everybody to keep on mute unless you want to ask something. And then you could unmute or you could type in the chat, either one of them, right? So the 3-phase tutorial, you all should have it. Let me just pull it back here so you'll see. We'll go through some of the things just orally. Did I put on the record? Yes. I did put on the record, yes? Yes. But right. So the first one, so most of these you should be familiar with already, right? The first one, briefly describe the difference between a phasor and a vector. This is actually something that is debated in academic circles, whether a phasor is a vector or not. Some people say yes, it is a vector because it satisfies all the mathematical definitions of what a vector should be. Some people say it is not a vector because really it is just a different notation for a sinusoid. Right? But of course, whether a sinusoid is really a vector, that is something that is another matter of debate, because you have vectors have direction and magnitude, and phasors have magnitude and phase. But the phase could act as some sort of direction. It does give you some sense of separation, you know. So what is it is actually a matter of debate. The thing that you have to know about it is where the difference becomes important is in addition and multiplication. So for both of them, when you add the vectors, you add the components of the vector. And similarly, for a phasor, you could, if you have something a plus jb, you could add the components of the phasor, right? So the phasors add end to end, just like vectors. The difference is in multiplication. If you multiply two vectors, let me pull this out here, right? If you have two vectors, 1, 2, and 3, 4, how do you multiply them, right? You have to either use, you can't just multiply them just like that. If I get MATLAB here, let me pull up MATLAB here. Right. So if I define two vectors, A is equal to 3, 4, and B is equal to 6, 7, and I multiply these, you'll see we get an error, right? Because you can't just multiply vectors like that. If you multiply matrices, you have to have the rows and columns lining up so that you could do the matrix multiplication, or you have to use something like the dot product or the cross product. These are specific types of matrix operations of multiplications. But if you had A was equal to 3 or 4 plus 5j, and B is equal to 6 plus 7j, which are phasors, complex numbers are phasors, then I can certainly multiply those two, right, and get an answer. So this is really where the difference is. The difference is in these operations like multiplication and so on, and that is really all you really need to know about it. So the big thing with phasors if you will remember, is for phasor, when we add, we usually leave it in the complex form. So if I have A plus JB plus C plus JD, that will give me A plus C plus JB plus D, right? And if I want to multiply, I typically leave it in the polar form. So I will have A angle, say theta A, multiplied by B angle theta B, and that is going to give me AB angle theta A plus theta B, right? And this is the powerful thing about phasors for use in AC analysis, this multiplication where we can simply multiply the magnitudes and sum the angles. Good. So that is basically all it is for that. There's no real definitive answer about what is the difference between phasors and vectors. This was just to get you thinking a little bit, right, about what is really the issue here. So, good. So on a single diagram, sketch the phasors for the following: 10 angle 0, 15 angle 125, 12 angle negative 100. So again, this is very simple. Now, sometimes people have difficulty sketching phasors, and I have no idea why, because literally all you are doing is drawing the line at the angle. So we start here. 0 degrees is considered to be in this direction, and then we go anti-clockwise. So 10 angle 0, we have what angle 0 here? We have this one, 10 angle 0. 15 angle 125, we have to go to 125 degrees. So we know this is 90 degrees here, and then we have to do another 35 degrees. So we're somewhere up here, right? And we're going to go, this is 125 degrees, and then we are going to make this 15. And then 12 angle negative 100. So again, we're going to go 90 degrees will be somewhere here, and 100 degrees somewhere here. And we have 12 here, right? So this is 15 angle 125, 12 angle negative 100, right? Good. So let's move on. Right. Briefly describe what is a balanced three-phase system. So this is quite simple. A balanced three-phase system is where you have three voltages. The voltages and the currents on each phase are all equal in magnitude and separated by a phase of 120 degrees. The importance of this is that it sums to 0. So remember, when we're dealing with three-phase systems, one of the benefits of the three-phase systems is that if you have three generators, say, and you want to connect a load to these, so you have one here, one here, one here. Oh, let me do it as a star, since that will be easier to see. Right? So we connect it to a load. Then the currents coming here all sum to 0. So I do not need a return path. Right? I don't need that return path. And what is the important thing about that? Well, this return path, if we are dealing with a power system, this return path is a conductor, would have to be a conductor. And if you think about all the places you have electrical wires and you have to put in extra conductors, you realize that is a whole lot of conductors, which all cost money, right? So That is, it saves money by simply not having a return, right? And it's not just one return. If we did it single phase, each one of these would have to have its own return, right? So we'd have 3 returns, and we don't want to, so it is as though you have a whole other circuit. You save half the conductor, basically, the whole return conductor coming back to your saving, right? So let's see, next one, sketch diagrams for balanced star and delta connected systems. Of course, the balance doesn't really make a difference here because we're not looking at the voltages and currents, so because it is circuit diagrams, right? So we just want to see the connections here. So we're looking at a star system, which is what I had up there. 1, 2, 3. They're all connected to the same point, right? You could draw them like that. You could draw them like this. Like this is also a star connection. Notice we have the same point here, all of them connected to the same point here, all of them connected to the same point here, right? It's all the same thing. And a delta connection would be end to end. So we have 1. So let's put a plus and minus here, minus plus, minus plus. Good. So we arrange them end to end. Or if you want to do it the other way, you could do it like this. 1, 2, 3. Right, and then you, oops. This one then comes back to the end here, right? So you basically have these 3 points. Or if you prefer, these 3 points. Right, this point here, this point here is the same point, all end to end. Good. So any of those things you could draw, and the important thing is how you make the connections. So for a star connection or a Y connection, the 3 negatives have to be tied together, right? 3 negatives tied together here, 3 negatives tied together here. For the delta connection, they have to be end to end. And it is the same for the loads. All we do is replace the source with a load, right? I don't expect any of these would have given you any problems, so we're just going through them quickly. Now we want to look at the phasor diagrams for these things. So if we look at the phasors for the Y connection, right? The phasor diagram for that is, we have, let me draw it in red. So let's look at the voltage. So let's look at the voltage on the for the line and then the current. So for the Y system, let's draw the system across here. Right, we have the I phase here, I line, and then we have across here is V phase, and here we have V line to line. Now notice we say I line and V line to line. That is because the I line is the current through the line, and voltage line to line is because it is the voltage between lines. So it is not line to line current, it is just line current. And it is line to line voltage. Sometimes you'd hear people say line voltage, and that is also acceptable because it is just short for saying line to line voltage. But you'll never hear anybody say line to line current because that is not short for anything. It is not long for anything. So it is meaningless, right? So here we can see that from this, we can tell that I phase is equal to I line, And we know that V phase, or V line to line, sorry, is the difference between the phases. And that works out to be √3 V phase. And let me put some magnitudes here. Actually, this one we can leave it without the magnitudes, right? This one is the magnitude. As we will see, when we start off, we're going to start off with the phase voltage diagram, the phasor diagram, and we will see what happens to these things with the angles and so on. So if we draw the phasor diagram for the phase voltages, that means this is 0.0 here, the ground, and we're just going to start from there, and we're going to draw the voltage, the phase voltage for each one of these. So let's take this one, and we're going to have here, let's call that VA. Then we have down here, that's a very good balanced looking diagram. So let's say here, VB, here, VA, here, VC, right? So it's rotating like this. So you get VA first, then VB, then VC. So you'll see here that if we want to look at the line-to-line voltage, this is the difference between these. So if I get the difference between these, VA minus VB, this is going to give me a vector going from B to A, right? And that is 30 degrees. And this is √3 VA, the magnitude of VA, right? Or VB or VC, doesn't matter, it's the phase voltage. Let's actually just call it that, √3 the phase voltage, right? In magnitude, if I want VB to VC, I will get a vector going from C to B. And if I want VC to VA, I will get a vector going from A to C. Notice these vectors go end to end, right? They go one into the other. And what do we notice? They're all 30 degrees from the vectors there. So this one here is AB. It is 30 degrees more than VA. This one here, so this one, let me put it here. This one is VAB. This one is VCA. This one is VBC. So notice VAB is 30 degrees more than VA. VBC is 30 degrees more than VB, right? So this is coming down here, which is 30 degrees more than this one. And VCA is 30 degrees more than VC. So we're adding 30 degrees to the vector, and we're increasing the magnitude by √3. Good. So that is for the voltage. For the current, we have IA, IB, IC, right? IA, IB, IC. But in this case, we have I phase is equal to I line. So we get them directly lining up. No change. Actually, let me draw that better, because that gives the impression that it's a different magnitude. It is the same magnitude. So it is exactly the same, right? So the line and phase current are perfectly aligned. They're the same. They're exactly the same current, because it is the same current that is coming up through here and going through here, right? The only difference is at this point here, we call it the phase, and at this point here, we call it the phase. And at this point here, we call it the line, but it is the exact same thing, right? So that is for the Y system. Now we move to the delta system. Any questions so far? Right, so for the delta, again, we're going to start with the phase voltages. So we're going to start with the phase voltages in the same way. right? VA, VB, VC. This time what we have is that V phase is equal to V line to line, and I line is equal to √3 I phase. So the opposite is happening now. So in this case, the phase voltage is the same as the phase voltage, that is the voltage across one phase, is the same as the line to line voltage. So we're going to get these ones overlapping here. Right? Just like we got with the current. And for the current, we are going to get the opposite happening. We'll get IA minus IB, right? IA minus IB, IC minus IA, and then IB minus IC here, which would give us the line currents IA line, IC line, and IB line. Good? So it's just the opposite. It is the analog to the star system with voltage and current. So both same sort of things, we just reverse the diagrams of voltage and current. Good? So next we have number 7, which is for a balanced three-phase system, 120 volts star connected with an impedance of 5 ohms, determine the phase current, the phase voltage, the phase current, and the line current. So what I did is I started this in MATLAB. So let me see if I find it here. And this is sort of what you'd have to do for your tutorials as well. This is the kind of, we're not going to do it in a MATLAB live script like this, but it is the kind of code you'll have to write. This is the level of code you'll have to write, which you'll see doesn't really qualify as code. It's really just using it to do straightforward calculations, right? So for number 7, we have balanced three-phase. Everybody's seeing this, right? Everybody can see the MATLAB? Yes, good. All right, so we have a balanced three-phase 120 volt line to line. Now, normally, if you're just given a voltage, it would be the line to line voltage. The standard is to give the line to line, right? So if you just see something and it doesn't specify if it is voltage or current or so, it means the line to line voltage. So, or it doesn't specify the current, it is the line current that would be meant. Good. So we need to calculate the phase voltage, the phase current, line current, and then we're going to repeat the thing for 3 plus J4 ohms. That is not watts, that is when you copy over from Word and it doesn't have the ohm symbol, it is capital W, it comes up as. So, right, so what information we have? We're going to enter it first. So I have the magnitude 120 volts. So this is the line to line magnitude is 120. The phase impedance is 5 ohms. And the other impedance is 3 plus J4, which we need for this part here. So I enter all of that at the start. Now, what do we know? First, we want to do it for a star-connected system. And for a star-connected system, we know that the magnitude of the line-to-line voltage is equal to √3, the magnitude of the phase voltage. And we have the line current is equal to the phase current. And note here for the voltage, I put in the magnitude sign because I didn't deal with angles. But here for the current, it is exactly the same, magnitude and angle. right? So you'll see that reflected. You'll have to take that into consideration when you do your calculations. So we have the phase voltage here, and we know the magnitude of the phase voltage just based on this is the magnitude of the line voltage divided by square root of 3. And I'm going to take the angle here as the phase as the voltage 0 angle, right? So that's what I'm going to assume here. Doesn't really matter what you assume because the question didn't tell you anything, right? So you could assume anyone. So just for simplicity, I am assuming it is 0. I phase is then V phase on R phase, right? Now, all the time when you're dealing with the phase voltages and currents, this will be true. You don't have to worry about your cosine thetas and all of these kinds of things once you're dealing with phase and phase, right? There is no, it is just a straightforward V over Z. So the power factor angles and so on will come when we start to look at power. So so we have here V phase is equal, sorry, I phase is equal to V phase over R phase. That works out to be 13.85 amps, and I line is equal to I phase, and that is 13.85 amps. There is no angle here because this is a resistive load, R phase, and we assume the angle is 0, right? So then there will be no angle here. This is the angle to 13.85 angle 0. Good. What else do we have to find? So we found the phase voltage, we found the phase current, we found the line current. Now we have to repeat for 3 plus J4. Well, it's exactly the same thing, right? Except now what we're going to do is instead of R phase, we're going to have Z phase. Good. So we still have to find V phase, which is the same. We have to find I phase, which we are finding the same way, except now instead of R phase, we have Z phase, which gives us this current here, and IL is equal to I phase, which is identical. Didn't have to add any 30 degrees or anything, right? If it was a voltage that I was looking at, then I would have to look at adding the 30 degrees or so, because in that case, the angle is different, but this one is identical, right? So what I did here for simplicity is I assumed the voltage phase, the angle at the voltage phase is 0. If I didn't, I would have to adjust it by 30 degrees. If I assume the line-to-line voltage is 0, then I'd have to minus 30 degrees to get my phase voltage. Everybody understands that? Right, based on our diagrams here, right? We see the line-to-line voltage was 30 degrees ahead of the phase voltage. So if I had assumed this line-to-line voltage here was the 0, then this phase voltage would really be minus 30. Good? So that is what, so instead of doing that, since we were building on the phase voltage calculations, I just assumed the phase voltage was really the 0, and I was just using the line voltage to calculate the magnitude of that phase voltage. All right. If nobody says anything, I assume everybody okay, and I'm just going forward. So for the next one, we're looking at the same thing except for a delta connected system. So all we have to do now is we're going to change, and for what we did for current, we're going to do it for voltage. So here we have the delta connected system. We have V line to line is equal to V phase. So you see here now we have no absolute values, just like in the current. The current here we had no absolute values. Here we have no absolute values. It is the one thing is equal to the next thing. And now the current becomes the one with the absolute values of the √3, which is what we had here for the voltage, right? And the same note as above, except now we have it with current. Good. So we want to find the voltage again. We're going through the same process. So this time, here we divided by √3 to get the magnitude. Here we don't have to divide by √3. it is exactly the same. We assume the phase voltage angle is 0 still, right? So V phase is equal to V line to line magnitude. That is 120. Both of them will have an angle of 0 in this case. I phase, V phase on R phase, which is 24, right? This will also be angle 0 because it is a resistance, so there's no phase shift. And I line magnitude, now we're just looking at the magnitude of this, is square root 3 multiplied by the absolute value of I phase. In this case, the absolute value is the same as the ordinary, as the full complex value because the angle is 0. But I've just put it in here for completeness. So that works out to be 41.5692 amps. Good. Now we change it. We're going to do the same thing again, but we're going to use Z phase. So we do the voltage, which is the same. We now find I phase, which is V phase on Z phase, right? This is an absolute value of 24. Now we find the angle. So we have this and minus 53. These are the angles of I phase. So we want the magnitude of the line current, which is root 3 by the absolute value of I phase, not the real value anything. It is the absolute value. So just 24 multiplied by I3, by root 3, sorry. We get 41.56. And if I wanted to find what angle this is now, I would have to add 30 degrees to this angle. So it would be minus 23.13 for the angle of the current, right? So, and again, that goes back to this here. If I have this is my phase current, and now I want this line current, which is IA minus IB, it is root 3 times the magnitude and add 30 degrees to the angle, right? This here is from the, here is 30 degrees. So if I drew that from the origin, it would be like, oh, that's not a good marker. It would be, draw it in orange, like that, which is parallel to this one here, right? And that would be 30 degrees. Okay, good. Sorry about that. So now we're going on to number 8, which is to describe the following terms: real power, reactive power, apparent power, and power factor. So the two that really give the description here, the first two, the real power and reactive power. So what is real power? Real power is the power that goes to do useful work. So this is the power that would be converted to heat or light or motion or whatever your end use is. This is what you want to transfer the power for, right? This is electromechanical energy conversion. So what are you converting the power to do, right? You don't just have electricity for electricity's sake, right? You want to do something with it. You want to run your computer, and your computer has some sort of electronic load, or you want to heat some water, or you want to shine a flashlight or whatever it is. There is some load at the end of it. The useful work in that, or you run an electric motor, whatever is the useful work in that, that is the real power. And the reactive power is the power which is in the electric and magnetic fields of the system. So within the system at different places, you'll have coils, you will have, or even on your wires that are not coiled, there is some inductance. The current generates a magnetic field, right? You get an electric field as well from the voltages. And if you have capacitors in the system or inductors in the system, it concentrates these fields. So the energy in these fields are what we call the reactive power. And the difference between these two, really, if you look at the graphs of power, let me pull this up here. if you look at the graphs of power, if you look at a graph for P for resistor, it will look like this, or graph of real power, it will look like, oh, sorry, not like this. It will look like this. Right, say I excite a resistor with an AC source, it will look like that. And all of this power is real, right? So actually it will be more like a rectified wave. It will be more like this, right? So all this power is above zero. So the average, the resistor then only dissipates power. If you look at it for an inductor or a capacitor, you're going to see this. So the average power here is zero, right? And we call that power Q, the quadrature power. So it is zero. So during one part, it is absorbing power. So power going into fields. And then during the other part, power is coming out of the fields. Right? So what is the point of these things? If the power is just coming in and out and in and out and in and out, why it all have them if the net power is zero? Well, we need these fields to transmit the power, as you will see in transformers and as you will see in motors. The fields are the bridges by which we transfer power from electrical to mechanical, or even from electrical to electrical, from one voltage level to the next or so. So we need these fields for the thing to work, for our systems to work, but they just cycle in the system. They don't actually get dissipated, right? And as you have seen from even ECNG 1000, when you have more of this reactive power in the system, to deliver a particular amount of real power, you would need more current. And if you have driving more current through the lines, you're going to have more losses in the line, right? I squared R losses. So even though you don't, the Q averages to zero, it results in a higher current in the system, which gives you more I squared R losses, and you'll have a less efficient system overall, right? And you could also transmit less power on the line because you will be transmitting a small amount of power, but you have a high current, which is going to heat up your line. And the lines have thermal limits, right? So that is why we always try to do power factor correction and so on and keep our power factors very good, right? So that is the real and reactive power. The apparent power is just the vector sum of these two quantities. And the power factor is the angle between the real power and the apparent power. And you know that from your power triangle, right? So we have S and P and Q, and this is theta, which is our power factor angle, right? And we call this case lagging power factor. And we always say P lags or leads S, right? So that's the way we always state it. So in this case, the system, we have S ahead of P. So P lags S. And then if it comes down the other way, this way, then we would say P leads S, if this is S here. P is always on the horizontal axis. Good? Right. So next, we have some more calculation questions. Let me see where I have my live script. Good. So we have for number 10, single phase 4 MVA system is operating at full load with a power factor of 0.8 lag. Find the real power and reactive power dissipated in the system. Of course, reactive power doesn't really get dissipated. It is only the real power that gets dissipated, right? So what is the information we have here? It is a 4 MVA system. It is operating at full load. That tells us what percentage of this 4 MVA is currently being used. So, and then we have the power factor, which tells us how that 4 MVA is split up between real and reactive power. So the percentage of full load tells us what percentage of the 4 MVA, and the power factor tells us how that is split. Good. So we have the, oh, this is the wrong thing I have here. It's 4 MVA, not 10. 4 MVA system, right? So the magnitude of S is 4, operating at full load, fine, right? So we have the power factor is 0.8, and we want P, and P is simply S multiplied by the power factor, right? Let me rerun this. So, which we get 3.2, right? 0.8 by 4 is 3.2. And then Q, we could find the Q in a number of ways. We could use our power triangle, right? And basically all of these things here are using the power triangle. So we could say we have P, Q, S. So we could say Q is equal to the square root of S squared minus P squared, which we will see here, right? Or we could say Q is equal to S sine theta, right? Our cos of the power factor gives us theta here. You know, the power factor is equal to cosine theta. So we have the power factor. So theta is cosine, is the arc cosine of the power factor. So we could use S by sine theta, or we could use P by tan theta, and all of those should give us the same things, right? So whichever way we do it, we should get the same thing, right? Next one, for 11, we have a Y-connected balanced three-phase 32 kV. So now here you have this 32 kV would refer to the line-to-line voltage. 32 kV, 10 MVA Y-connected system is supplying full load at 0.8 power factor lag, and you have to find the phase current and the where the end of this thing went, right? We need to find the phase current and the real and reactive power. So again, here we put down our information, 10 MVA, V line to line 32 kV, and the power factor 0.85. Now we want to find the phase current. There are a number of ways we could go ahead and do it. So, and you'll see them down here. So first I found the S per phase, which is just 1/3 of the total S, right? Because it is a balanced system. So each phase will be equal in magnitude. So just simply divide by 3, get the per phase. Then I want the voltage per phase. So the magnitude of the per phase voltage is the line-to-line voltage divided by √3 because it is a star system. So I got my per phase voltage, and then the power per phase, I found it as S, the S per phase magnitude multiplied by the power factor. Remember, S, P is equal to power factor by S, right? So I get the per phase quantity there, and then I could find the current in different ways. I could say, I could use the equation P is equal to VI cosine theta. Of course, cosine theta is my power factor. So if I rearrange that, put it back here. So if I have, so I have P is equal to V I cosine theta, which is equal to V I. This is V phase, I phase, right, by the power factor. So rearranging that, I get I phase is equal to P phase divided by V divided by the power factor, divided by V phase divided by the power factor, right? And that works out to 180.4. Or I could also use the equation S is equal to root 3 V line to line I line. Good. So then I use, this is the three-phase power, S three-phase, right? So you see I use the full three-phase power, S mag, divide by square root of 3, divide by the line-to-line voltage, which is the 32, not the phase voltages. These are the line-to-line quantities. And I get the line current. And since this is a star system, the line current is equal to the phase current. So it will be the same as the phase current, and it works out to be the same. Or I take the phase current as just the magnitude of the single phase apparent power divided by the voltage, and that one is S is equal to VI, which of course comes from S is equal to VI conjugate, and just the absolute value of that gives you this, right? And if I do that, I find it, and all of them are exactly the same. So you can see there are multiple ways you could work it out. And then to find the Q per phase, I just, again, I'm looking at a power triangle, so there are multiple ways I could do it. And in this case, I just went with the simple Pythagoras theorem, square root of S squared minus P squared, right? And I end up with this. Good. Last question. I have a balanced three-phase system, 25 MVA, 40 kV delta connected system, supplying 0.75 full load at a power factor of 0.6 lag. So again, 0.75 full load tells us what percentage of this, and the 0.6 lag tells us how it is broken up. So the magnitude of S is 25 e to the 6, 25 MVA multiplied by 0.75. We have a line-to-line voltage of 40 kilovolts and a power factor of 0.6. So I find here now the line current, which is, here I'm using this one, right? S is equal to root 3 VL IL. So IL is S divided by root 3 divided by the line-to-line voltage. I get 270.6. This is a delta system, so the magnitude of the phase current is 1 on root 3 by the magnitude of the line current. So I find that, so I just divide by square root of 3. I want to find here the, so that is my phase current. I want to find, so I got the phase current, the line current. Now I need to find the real and reactive power. So I find the single phase power, just divide the power by 3, and then I could find the single phase P by simply multiplying that by the power factor, and I could find the Q by just using Pythagoras' theorem again. Good. And that is it. Anybody has any questions? Any questions? I guess everybody should pretty much be okay with this because you'd have done this really in 1015. So it should not have posed too many problems. Okay. S mag stands for the magnitude of S, which is the apparent power. So you'll see here, it tells you the power here is 25 MVA, but it is at 0.75 full load. So the magnitude of S, which is the magnitude of the apparent power, is 25 MVA multiplied by 0.75. Right, just I'm seeing somebody writing before that. Can we always assume the phase angle is 0 on the line to line? Yes, you could assume that unless if you're not told anything, that is the easiest thing to assume, right? So it really makes no difference. Most of the questions will really be concerned with magnitude, and a lot of your calculations as an engineer in power systems, you'll be concerned with the magnitude for certain things. You might be concerned with the angle for other things. So a lot of times you just want to make sure there are no over voltages and so on the system. So it is the magnitude which concerns you more. This is not to say that the angle is not important though, right? Of course, you need to know the angles, especially if you're doing things like matching transformers. If you're putting two transformers in parallel, you have to make sure, even if you put one in, if you have one in star and one in delta, you will get a phase shift. And then if you connect them in parallel, you're going to get circulating currents in the transformer because they're going to be at different angles, right? So just to show you what I mean by that is, suppose you have two transformers, right? One is so you have a delta to Y. Let me, right, let me do like this. Right, so you have a delta Y on this side, and on this side you have, oh, let me just draw it simpler. So let's say you have a Y to delta here, and you have a Y to Y here, right? So this is your transformer. These are your two transformers. Now on this side, if you have here VA angle 30, and you have here VA, you get here, say, N, which is your turns ratio, VA angle 30, right? It maps phase directly onto phase. Good. So the line-to-line voltages, everything here will be the same. The only thing that will be different is the magnitude. Right, so let's say you connect it to the next one here. You have these two things in parallel. So you have VA angle 30 here as well. Here you're going to get the same and VA angle 30. Good. Now, when you connect these two things, the line-to-line voltages here are going to be the same. The line-to-line voltage in this one and the line-to-line voltage in this one is going to be the same. So everything is fine. It's the same voltage. But if you had a delta here instead, right, then, and you map this one to this, NVA angle 30. Now your line-to-line voltage here is still NVA angle 30, while here your line-to-line voltage is NVA angle 30 multiplied by square root of 3. So you're going to start getting problems, right? When you connect these phases together, they're not going to be the same. So you're going to have current starting to circulate inside the transformer. And that's not something you have to know for this course. That's not something I'm just telling you why you have to know what the why the angle would be important in different cases. Right, an example of that. Good. So you could forget that for now. That is just why it is important to note down the angle. Well, one of the reasons why. So, any other questions? Okay, so you will have for this week, I think we don't have anything scheduled this week. Next week, we're going to start looking at the transformers. So that is when your transformer module will start. I will post up the tutorial and so on. And next week, what we will do is, you don't have any work due next week, but next week, what we will do for class is I will go through the method of how to submit answers for the tutorials and how to check to make sure you have no syntax problems and all that sort of thing. Okay, so that when you submit your tutorials, you could be sure you're not leaving out a bracket here or there, something mismatched, and you end up getting penalized for syntax error as opposed to theory error. Good? Okay, everybody's okay? All right.
Yes, sir. I have one question.
Right, good.
So when the MATLAB assignments begin, regarding the names of variables, will you have like a standard
I
or
will
something?
tell you all, the question will say what the variables are.
Okay.
So you
Thanks,
have,
sir.
let me bring that back up again and show you how it was for circuits. So you'll have an idea. Where is it? Right, so this is the circuits paper, right? So you'll see it gives you here, and it tells you the nodal equation of each node can be expressed in the forms, blah, 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 and specify these things, and it tells you what the MATLAB variables are. And these are all case sensitive, right? So then you would see in the solution sheet, say, let me see when that solution sheet comes up. Okay, the solution sheet is not loading. Not loading my Excel. Here it is. So you'll see, for example, here, it will tell you node A 0 is equal to whatever. So you'll know that you have to, and here you have VA, VB, VC, VD, which are the things that the question asked you to have, MATLAB variables, right? So the next question will tell you what the MATLAB variables should be, and you should be able to figure it out from the wording of the question. The question will be worded a little bit differently, so hopefully it will be explicit, right, as to what the variables are and so on. Good?
Okay.
And basically you'll be entering it like this, right? And then it's a simple matter to check whether these things are correct MATLAB syntax. So I'll show you how to do that in MATLAB so that you could make sure that when you enter it, you know you have no syntax errors. Right, somebody's asking, go over the real and reactive power per phase for number 12. Okay, let me find that. Right, so what we have here is we found the line current and line voltage. We know, so we want to find the real and reactive power per phase. So we know that the apparent power is this. We know the power factor is 0.6. So per phase, it will be 1/3 of this will be the apparent power per phase, because this is the 3-phase apparent power. So to get the apparent power per phase, we simply divide by 3. So now we have, since it is a balanced system, the 3 of them are equal. P per phase is simply the S multiplied by the power factor, as you have for everything, right? So we do that in some other places too. Like P is S multiplied by the power factor, right? So S multiplied by the power factor. And Q, then we're looking at our power triangle, right? So we have our power triangle. P, S, and Q is equal to the square root of S squared minus P squared using Pythagoras' theorem, right? And that's it. We get P and S, and sorry, Q per phase. Good. Okay, so that is it. And I will see you all next week. And we should have the lab schedule and so on up by then. We still have some registration issues going on. So hopefully all that should be sorted out. But you all know Andrew Balgovin. So he is the person in charge of the labs. If you have any things you need to sort out in the meanwhile, if you have any special requests because of clashes in particular classes or so, and you want a particular, well, you don't need lab slots and so on this time because everything is online. So that shouldn't be a problem. So forget that. So yeah, 100% coursework. We didn't hear anything about that from the university yet, but that is what I am planning for, right? Yeah, the coursework could be the mini project. I will give you that in a few weeks' time. So again, it would be the mini project to be building on what you already did. So from the lab, you'd have done some simulations and so on with Simulink. And for the mini project, we're going to build on that, but you're going to do it like with an application. So the idea is that you get to know a little bit more about what you would do if you had to spec a motor for a particular application. And this application could be like an electric vehicle, it could be a drone, it could be a pump, something like that. And then you have to know a little bit about the physics of the environment. How do I know what torque and power and so on that I need to know? So it is an independent study project, but I will put some resources for you to use. This will also tell you about where you could get resources, because you just can't go online and pick up something from a forum and use that as a resource. You have to make sure the resources are good. So you'll have to look at things like application notes from places like maybe Texas Instruments or motor manufacturers. Look at their spec sheets and see what are the types of things they specify for the motors, right? So that would be the idea, so that you learn a little more about the practical side of specifying the motors. Okay, good. Yes, the solutions will be, the videos will be posted for every class. I will put it up, just have to convert it and post it up on YouTube. And then I'll put up at the bottom of the My Learning portal somewhere, I will post the links to the classes. Good. And the projects are also group projects. So I think we talked about that. So you'll have to, based on your application, you'll have to look at something with spec out an induction motor, a DC motor, or synchronous motor, and then you will have to look at the performance of these. So you could give, so one person could look at getting the torque specifications and so on. One person could look at the induction motor, one person could look at the DC motor, one person could look at the synchronous motor. So it will be easy to break up the project like that, so it will be manageable. Good. Okay, and you could expect to have to do a little bit of peer marking as well, so that you all could pull up each other and make sure everybody doing their work. Good.
So just before you leave, so the group project, it is assigned, or like, I mean, the members.
Yes,
is it assigned?
Yes, you'll be assigned to groups.
Okay.
Yeah. Okay. Any last questions?